We now know that SDVoE is the only truly interoperable standard for matrix switch performance across a 10 gig network. And at the heart of this interoperability is the API, or Application Programming Interface. This course will give you a deeper insight as to how the API guarantees the interoperability of different endpoints from different manufacturers. Let's begin with the acronym SDVoE. It stands for Software Defined Video over Ethernet. Video over Ethernet is easy to understand. It's video distributed over a standard networking infrastructure, or Ethernet. But what does this software defined part mean? To explain this, let's compare a software defined topology to a matrix switch topology, or as we like to call it, hardware-defined topology. In the hardware-defined world, we rely on the matrix switch to manage all the routing, configuration and control of the AV signals. And in the software-defined world, this is all done with, well, software. Anyone heading to the SDVoE.org website will see the mission statement, and many key words will pop out, such as manufacturers, designers, integrators, technology managers, Ethernet, AV distribution, interoperability, standardization, SDVoE platform, user experiences. And it's this which demonstrates the power of the SDVoE platform. AV equipment and service providers working together to deliver experiences to end users, which are both standardized and fully interoperable. So what exactly is the SDVoE platform? To best answer this, think of SDVoE sitting on top of two key technology components, a family of networking technologies known as 10 gig Ethernet, and another technology component called Blue River, which takes care of all the AV routing and processing. Now, thanks to Ethernet being around for over 40 years, we already have a pretty clear understanding of what it does. But what is Blue River? Blue River. Oh no, that's not it. Here it is. Blue River. It's a technology supplied by the Semtech Corporation, a founding member of the SDVoE Alliance. It's a chip which standardizes AV distribution and control over Ethernet, and it's this platform which guarantees the interoperability needed for designers and integrators to build those truly customized user experiences. The Blue River platform itself consists of two components: the Software Application Programming Interface, or API, and the hardware called the Blue River chipset. Together, the Blue River chipset and the Blue River API are tightly coupled. You cannot talk about one without the other, and it's this coupling which the SDVoE Alliance has adopted, and we refer to this as the SDVoE API. Let's remind ourselves of a typical SDVoE topology. A 10 gig Ethernet switch in the centre, SDVoE transmitters or encoders connecting AV sources to the switch, and SDVoE receivers or decoders connecting the displays to the switch. Inside every SDVoE endpoint is a Blue River chip, and it's this chip which is able to convert the original source signals into a network stream, as well as reconstruct those network streams back into their original format ready for the displays. This is important to remember because regardless of which manufacturer made the endpoint, every data stream being generated by a transmitter or reconstructed back into the original format by a receiver is done by the Blue River chip. However, this process alone does not guarantee interoperability, because it doesn't address many important fundamental parts of an AV distribution system. Even though the same chip is present in all SDVoE hardware endpoints, the chip itself doesn't address things like device discovery, device control, device monitoring and health, or controlling of the routing and streaming and which stream goes where. Is it for multi-view? Is it for video wall? Is it for matrix switching? Important features like starting and stopping streams, extracting audio, or even EDID management are not addressed by simply having the same chipset present in each endpoint. And this is where the SDVoE API comes into play. Think of the SDVoE API as the missing piece of the puzzle. It's this API which takes care of device discovery and monitoring, controlling AV routing and switching, configuring, cropping, scaling and programming, audio extraction, EDID management and control signals such as IR and RS-232. In order to manage all of this, the SDVoE API is implemented as a software service or control server which lives on the network. Every SDVoE system will include at least one SDVoE API control server, which could be hosted by a computer, a web browser, or even a mobile application. These hosts contain the software which connects to the API service, allowing the user to control the SDVoE devices on the network. From a technical perspective, you can think of this API service as the abstraction layer between the application providing the user experience and the SDVoE hardware endpoints connected to the network. But what's an abstraction layer?
In computing, an abstraction layer or abstraction level is a way of hiding the working details of a subsystem, allowing the separation of concerns to facilitate interoperability and platform independence.
Let's put it another way. This means that the API service which implements SDVoE abstracts the whole system, including the network, the endpoints, the sources, and the displays, and it turns them into virtual constructs, each with defined rules, capabilities, and behaviors. Therefore, every application software written or custom graphical user interface created on a computer, a web platform, or the mobile phone device is fully agnostic and wholly dependent on the hardware itself. Here's Helgi Sigurdsson from Semtech to explain this technical process in more detail.
So, the SDVoE API itself, the syntax comes in two distinct flavors, and this is up to this is the choice that someone who is writing this experience software makes in the beginning. So this API service, or the server that that the user experience, the user interface is talking to, it can either be done over a standard text, very simple text style command line interface, or it's possible to use a REST style API syntax that uses WebSockets in addition for asynchronous events, like something happens on an endpoint and a notification has to come back to the user software about something like a HDMI cable got disconnected. That's a synchronous event. So REST API by definition is always one way. There's a command, there's a reply back, but sometimes there are these events, asynchronous events that occurs as well. So therefore this REST API or the HTTP interface also implements this WebSocket. But regardless of which syntax is being used, the responses from these commands, regardless if it is a REST API command or command line interface command, the responses, the reply back for these commands are always going to be in the same format, and the return of every command is basically in a JSON format. And the example on the right-hand side, there's an example of a typical JSON return. And actually this is a return for get identity, getting the identity of a device. Like what kind of a device are you? Are you a transmitter, are you a receiver, etc.? What are your capabilities? So just another example of a command. So for example, a command that is just to send a video from an encoder to a decoder. So the text format is quite simple. It's a join. You use to device ID and you specify in what kind of a stream you are generating between this encoder and a decoder. The HTTP format of the REST API is a little bit fatter. It is more verbose, but that is just nature of the REST API or the HTTP format. It's more chatty than a standard command line interface. But in this case, we are basically saying this encoder, the video that is coming in on the HDMI port number 0 is being routed over the network to a receiver, and we are going to do this in a genlock mode, which is this low latency mode that is guarantees under 100 microseconds latency. Another example here is to, like for example, you started a stream and you want to stop it. Just a stop command. In this case, you're sending it to a transmitter or an encoder. So I want to stop this stream that you are generating from this HDMI source that is connected to port number 0. So in summary, so every SDVoE endpoint includes a Blue River chipset. Every SDVoE system includes an SDVoE API service. The combination of the two forms an abstraction layer that is hardware agnostic. So any application or experience user interface or graphical user interface that is used to control your system is basically coded against the API, and it by itself it's hardware independent. And therefore, and because of all of this, every SDVoE endpoint that has this Blue River chipset is basically interoperable with each other and can be controlled together with other endpoints using the SDVoE API. Another perspective of this is basically the OSI model. The SDVoE platform basically covers all 7 layers of the OSI model, so this is a full stack solution. Layers 1 and 4, the physical, the data link, the network, the transport layer. I mean, those are not invented by SDVoE. These are being used by SDVoE. But the other 3 layers, the layers 5 to 7, they are defined by the SDVoE chipset and the API. So this full stack implementation is the one that ensures interoperability.